Welcome everyone. My name is Chris Friedemann and I'm the Chief Commercial Officer at NEOS. In this brief presentation, I would like to share some insights that have been learned from collaborative efforts with a few of our clients regarding the impact of basement on oil and gas exploration. A valid question that one might ask is, why is understanding deep crystalline basement important when developing oil and gas exploration strategies? As it turns out, basement can have far-reaching controls throughout geologic time and throughout the geologic column. For example, consider an undulating basement topographic surface upon which sediments are deposited. A thicker sedimentary sequence will be deposited in the basement topographic lows compared to the areas of basement topographic highs, hence impacting aerially the thickness of the stratigraphic column. Regarding basement composition, multiple metamorphic and intrusive events result in mappable compositional variations. These multiple events result in aerial variations in thermal regimes and different proximities of source rocks to heat sources. Basement faulting, often originating from Precambrian time, provides zones of weakness conduits along which younger intrusive emplacement can occur. These younger intrusions may be contained within basement or intrude into the overlying sedimentary sequence. The zones of weakness conduits are also migration paths for hydrothermal fluids. Although basement faults originate below the sedimentary sequence, they are often reactive and propagate upward into the stratigraphic column. Intrusive emplacement and basement-sourced faulting generate structural pop-up blocks and create or enhance natural fracture networks in source rocks and/or reservoir intervals. This slide from the Neuquén Basin in Argentina shows an example of how basement topography controls sedimentary deposition. The image on the left is the basement topographic surface derived from multi-physics 3D modeling. Areas of high relief are depicted in warm colors, while areas of low relief are shown in cool colors. The image on the right is the Vaca Muerta shale isopack, also derived from the 3D modeling exercise. Thicker shale sequences are depicted in warm colors, while thinner sequences are shown in cool colors. Note the direct correlation between low relief basement topography and thicker Vaca Muerta sequences. The ability to identify thicker shale deposition as well as depth of burial is an important part of an oil and gas exploration program. Moreover, if crystalline basement serves as the primary conduit for heat that will cook the source rocks above it over geologic time, knowing the locations of basement highs and lows can impact the relative thermal regimes in the basin as well as the resulting liquids content from individual wells. Basement topography is not always easy to determine. This example, from the Denver-Julesburg Basin in Colorado, shows how traditional horizon mapping from well logs may not provide adequate insight. Very few wells penetrate basement in the DJ Basin, so a basement horizon map generated from sparse wells, as shown on the left, results in a generalized, smoothly varying surface. By invoking a multi-physics 3D inverse modeling approach that incorporates well penetrations as constraints, we generate a vastly improved image of the complex nature of basement surface. Oil and gas exploration programs rely extensively, almost wholly, on seismic imaging to provide subsurface insights. While the seismic method is excellent for stratigraphic and structural mapping for reservoir horizons, information about crystalline basement is often limited given the physical attenuation of acoustic waveforms that occurs with depth. Even if basement geometry can be obtained from seismic images, information about basement composition is fundamentally lacking. NEOS utilizes a multi-physics approach to model building by incorporating all available seismic, well, and geologic data with airborne gravity and magnetic data. This methodology allows us to generate data-honored 2D cross-sections and 3D Earth models. A benefit of this approach is that multiple physical properties such as acoustic, density, susceptibility, resistivity, and gamma ray can all be taken into account. This approach begins with the generation of a suite of constrained 2D cross-section models throughout the study area, one of which is shown here. In this 2D model, the basement is shown in purple, while intrusives are depicted in orange and magenta. Faults are also shown, in some cases extending from the basement to the reservoir intervals above. Horizon surfaces across the suite of 2D cross-sections are generated to obtain an initial starting model for the 3D inversion process. This inversion produces a constrained, data-honored 3D Earth model that can be interrogated to evaluate basin architecture, structure, stratigraphic sequences, and basement composition. Multiple methodologies can be invoked to map basement composition, as illustrated in this example from the Appalachian Basin in Pennsylvania. The colored basement surface, obtained from the 3D multiphysics inversion process, was modeled to obtain generalized lateral variations in magnetic susceptibility. High susceptibility values are depicted with warm colors, while low susceptibility values are shown in cool colors. Subsequent to the horizon-based magnetic inversion, a volumetric magnetic inversion was performed to yield the 3D voxel representation of the susceptibility variation shown beneath the basement surface. As expected, the two independent models are complementary. The high susceptibility body cutting across host rock basement is interpreted to be a younger intrusion and placed along a pre-existing zone of weakness as described previously, potentially along a failed rift zone. In addition, a 3D point source inversion was performed. The solutions plotted as black dots, identifying contact margins and interpreted fault and fracture zones. While the intrusion and placement occurred along a structural zone within basement, the event creates fracturing and rock preparation for hydrothermal fluid migration into the overlying sediments. Shown here as proportional symbol plots are Marcellus shale oil production in green and gas production in red, draped on the modeled basement composition and zones of weakness. The purpose of this exercise is to illustrate the causative effects of events occurring within basement on the occurrence and relative BTU content of hydrocarbons in the overlying reservoirs. Returning to the DJ Basin, the relationship of basement faulting to reservoir production, in this case from the Niobrara Shale, is further substantiated. This two-image set shows how basement-controlled structural domains correlate to producing field areas on the left image and oil production on the right side. The best Niobrara oil production occurs within basement-controlled domains. Zooming in on the Hereford and Pony fields within the DJ Basin, the impact of basement structure and intrusive activity can be evaluated in greater detail. Interpreted basement faulting is shown with the black lines, as are interpreted intrusions, which are depicted in red. The Hereford field is located above an interpreted basement intrusion, which can be seen clearly on magnetic data, which is not depicted on this image. The Pony field is situated along an interpreted pop-up feature in the basement, presumably caused by two nearby interpreted intrusions. This evaluation shows that not all fields are situated within equivalent geologic environments, and that a rigorous analysis is required to assess all potential target areas. I hope that this presentation has successfully demonstrated that basement, while often separated from source and reservoir rock by great distances, plays an important role in casting the setting for the development of hydrocarbon systems and their economic potential. Whether it's a structurally derived impact such as the relative thickness of sediment within a basin, or a thermal impact driven by proximity to basement, compositional variations in the basement, or proximity to intrusives or fault-related hydrothermal fluid migration, the basement plays a key role in hydrocarbon generation and regional prospectivity. Thanks very much for taking the time to listen to this presentation today.